is a feasible option, but I prefer not to. So who dares to say that a week is too short? Really? No, you dare to say it, but you don't mean it, right?
Yeah, I mean,
you mean it. Why? Because you have many other things to do, or just because you're afraid that a week is not enough?
other things to do.
Yeah.
Like 2 hours and
Yeah, yeah. I was afraid of that. This is not the only course.
No,
I do really like it. Okay. I'm hesitating because it's, I mean, the order as I made it is for a reason. It's better this way. But if it's not possible, then we go for the next best option. Okay, how about a compromise? For now, we leave the deadline in a week from now. And if you find out, say, by mid next week, that that's too early, let me know, because then we still have the option to change the order of the lecture. Does it sound like a reasonable plan? For all the others, it means that you, well, maybe working too quickly, too fast, too early, find out only later, but that's not really wrong. Okay? The other thing is, and I'm looking, is tin here? Yeah, no, right phone. I'm putting up tin for adoption. He's the only one who's not in the group. And we have all balanced groups, so consisting of 3 persons. And I discussed this with Bart Romein, who will do the correction work. We think it's best to make one group of 4 instead of splitting then such a group into 2. So any group that's willing to adopt Tim, yeah, you're happy with that?
Yeah.
Yeah. Okay. So that problem is solved too. All right. Anything else that we need to discuss before we can go to the contents? Oh, maybe did you last year participate in those assignments?
No, not really. I mean, we started on the first one, but I stopped like halfway during the...
Yeah, okay. So there's no restriction on the assignment I should give to your group? No. Okay. Maybe you get lucky. Yeah. All right. So indeed, talking about those assignments, shortly after this lecture, I'll indeed make this assignment, definitely by this evening. So indeed, you have more than enough time. Talking about assignments, this is all for information. The other thing that will be assigned to you is the case study. Now, the issue with this block of lectures is that right in the middle there is this careers week, or what do we call it nowadays. And I'm fully aware that I'm not supposed to assign any work to you during that week because you need to be working on your careers. If I would do otherwise, I would get serious trouble with the program director, so I won't do that. But there's nothing that could stop me from already making the assignment of case studies just before that week. So that's what I plan to do on, well, in exactly a week from now during that lecture. The thing is that it's probably a good idea that you read about those case studies. There are, I think, 9 of them, so that you can make an informed choice. Yeah, so my suggestion is have a look and together with your group mates come up with your preferences, and then that will be used as an input in a very nice procedure of deciding assignments of case study. Okay? Now we can get started. Okay, so the first subject of today is something that we've been mentioning every now and then as more or less a natural extension of the brief course rule that we've been looking at so far, namely the two-stage case. And as in the two-stage case, also here our starting point is just a linear program. But it's a linear program which has a nice structure reflecting that the decisions, so factors x1, x2, and so on, can be given interpretation as corresponding to time stages. And then the structure of the problem tells you, okay, we have decisions for stage 1, x1, and for x2, for stage 2, all the way up to some horizon, some fixed number of time stages. I use h to indicate it. And for each of those vectors of decision, we have constraints, and the structure is, as we see in quite a few applications, indeed only coupling neighboring time stages. So the interpretation of this model, this linear program, is the decisions of stage 1 limit what we can do in stage 2. So indirectly actually also in later stages, but the direct influence is only between neighboring stages. Maybe you've seen examples of such a staircase structure before. Now this is on itself already an interesting model. It has many applications, but for us it becomes more interesting because some of the data involved in this problem that I summarized by Xi, I also could have called it omega. Of course, we will give the interpretation of any random data. Uncertainty is also involved in this multi-stage problem. Okay, so that's the starting point, and now of course we need to think about how could we give this a meaningful extension to make it into a nice optimization problem. Okay. This is another perspective, namely from that information point of view. As I mentioned on the previous slide, we will assume that to each stage there is random information connected, meaning that at various moments in time we will get additional information, namely corresponding to that time point. And that's similar, but not quite the same, as we've seen in the two-stage setting. Namely, in the two-stage, and you're very familiar with it right now, the idea is that we need to take a decision now under probabilistic information about the future, and then later, depending on the realization of the future, we get such a recourse opportunity. We can repair infeasibility. So the structure, the order of things is that we take a decision first, then we do an observation, and we may get another decision. And underlying all this is a tree describing the information structure. Well, to call this a tree is maybe a bit fancy, better call it a bush or a fan or whatever. But it describes indeed the information structure. Namely, at time now, we fully know the information relevant to the situation. That is, there is no uncertainty now. But in the future there is, and there are a finite number of scenarios in the example I'm giving you. I know we could also make it more general, also considering continuous distributions. But for this context of multi-stage problems, I'll talk about discrete distributions only. So I hope that you recognize that this then is a nice description of the problem we're looking at. And we know that what it calls for is actually a collection of optimization problems, namely one corresponding to the first stage, and for each possible realization in the future, a corresponding second stage problem. Now, underlying all of these are LP formulations of the problem, but we do know that, well, as a consequence of the fact that we also have these second stage problems, actually the problem that we're solving in the first stage has this Q function, expected to equals cost function, which is non-linear, but convex. Yeah, so that's the structure. And now we make a step to more than two stages, so multi-stage. As soon as it's free, we call it multi-stage. And it's very similar in structure. Indeed, like in the two-stage, we have this sequence of decisions and observations. And now the thing is that there are multiple. Actually, one decision corresponding to each time stage, and we call it the time stage because we get new information. So indeed, decision, observation, decision, observation, until the time horizon. And, well, you could think about multi-stage problems involving continuous distributions describing those future scenarios. But that's a bit advanced. Let's keep it simple. That's already difficult enough. In the multi-stage setting, typically we only talk about discrete distributions. And then the corresponding picture of that information structure is indeed a tree. And the tree starts at the root, and such a line all the way, such a path all the way up to the horizon describes one particular scenario, that is, one realization of a future. And the structure is indeed that, okay, first time instance, we are at now, And then at time equal 1, we may, in this example, have two distinct scenarios. But at later time stages, those scenarios again diverge depending on the new information that we receive. So altogether, that indeed describes such a scenario tree. And I'm guessing that to also from this concept, this kind of picture is quite familiar. You've seen that before. All right. So that's the underlying information structure, like in the two-stage, but, well, an extension. Like in the two-stage, again, at every node in the tree, we allow decisions to be made. Namely, depending on what we observed so far and under uncertainty about the remaining future. In terms of the tree, it means that in every node there is such a decision problem. And correspondingly, we take a decision xt at stage number t, depending on the node that we are. So, at this time stage, there are actually two optimization problems. At this one, let me count, there are 5, and these are 12 or so. So, lots of decision problems, but all, again, in the same vein as we've seen before. Indeed, at, for instance, this node, we are solving the problem which is constrained by linear constraints and having corresponding to that stage linear costs, but also expected costs with respect to the remaining future. And that's very similar to what we are typically calling that recourse function Q. It's now not about just the next stage, but about the remaining future. And the message is that structure in that sense is quite similar to two-stage problems. All right? Let's take a closer look. Indeed, at every node, the following happens. Well, except for the very first node, which is slightly different than the nodes at the time horizon h, but all the nodes in between at least are all the same. We get new information. That is, we get information on the random parameters corresponding to that particular stage. And then we need to solve an optimization problem using that new information, but not knowing, other than probabilistically, what the future will bring. So that's reflected in the structure of the problem. We're minimizing, maximizing of course, but we always talk about minimization problems. To find the best decision for that node, given what we know, given our history, and with the probabilistic information of the future. That is, we have a first term in the objective, which is linear in linear cost in the decision that we make now, but that decision also has consequences for the future. And that's suggestive notation, of course, again, a function Q of the current decision X. So that's expected future cost. But we're not entirely free to make those decisions. There are constraints, and they capture the dependence on, well, the history. Like we have in a two-stage setting. And we compensate for deviation. Well, the constraints here are of much the same nature. Namely, we have a history, in particular the previous stage, and if you look at the tree, for every node that so-called ancestor is actually unique. So we can talk about the particular decision X, notation values, T minus 1 in the ancestor node, H of K. And that's what comes into the constraints. And like I said, the Q function is about the expected future cost. And this is how the various decision problems at the various nodes are connected. And I know it's not great to discuss it like this, but my point is that I want to make clear to you that it is to some extent similar to two-stage problems. And if that's clear, then I'm happy. And so that's the point. Another perspective is to say, well, given that all those nodal problems are very similar, like in the two-stage case, described by those, well, linear programs plus polyhedral function in the objective, it shouldn't come as a surprise that like in the two-stage case, it's not too hard to see, show, that actually such a multi-stage Peacock problem is again just a linear program. But whereas the two-stage problem was large, the multi-stage problem is huge. That really exploded because typically, the more stages we model, the more refined modeling we use, the larger the scenario tree, also in terms of the nodal